Hi, everybody. Thanks for coming today. My name's Emma O'Neill. I'm a structural engineer at PTL Structural and Fire, and I'm one of the members of the Timber Design Society committee for this year. So before we get into today's webinar, we're just going to run over a bit of housekeeping and upcoming events coming your way from TDS. So the next seminar in our 2024 webinar series is going to be by Thomas Lim from the University of Canterbury, and he's going to be talking about manufacturing and quality assurance of CLT. So look forward to that on June 20th. And then in the future, we've got a presentation from Xiling Pei from the US, who's here at Canterbury at the moment, doing a presentation about tallwood project findings from the world's tallest full-scale shake table test. So that will be the webinar in July. We've got a few upcoming topics about lessons learned on mass timber projects, carbon and sustainability. And as always, if anybody has any topics that they're interested in learning more about, or if you have any topics that you'd be interested in presenting on one of these webinars, please feel free to get in touch. Always looking for feedback on that. A few other events that we've got coming up. As I mentioned, we're lucky to have Xiling Pei in New Zealand at the moment, teaching a course at University of Canterbury. And we've scheduled an upcoming panel discussion and presentation about mass timber buildings in New Zealand and in the US. So there is going to be a presentation in Christchurch on June 5th, to be confirmed. We may not be able to stream that for anyone outside of Christchurch, but we are planning to do a recording, so that will be posted and available for everyone to watch. There is an upcoming CSOC seminar on timber design that will be various cities around the country from July 22nd to 31st, and that is all about durability and moisture management of timber and realizing design impacts on build costs of timber buildings. And the last thing, TDS is going to be putting out some research scholarships for students involved in timber engineering and research. So if you are a student, keep an eye out for that. You'll be getting an email about that shortly. As always, we want to thank our sponsors, FutureBuild, MyTech, Simpson Strong Tie, XLAM, iBuild, and Rothoblast. Now on to today's webinar. Today's presentation is going to be about troubled timber connections by Pierre Quenneville. Pierre is a professor of timber design at the University of Auckland. A structural engineer specializing in timber structures, Pierre's expertise is with timber connections. He's participated heavily in the development of the recent New Zealand Timber Code, specifically about connection design. His research work is mostly on the brittle failure modes of timber connections, and more recently, he's concentrating on resilient connections for structures. In this presentation, Pierre is going to highlight some of the issues with timber connections that he's observed over the course of his career and provide some recommendations as to potential alternatives or remedial measures. So thank you very much, Pierre, and take it away.
Thank you very much, Emma. Welcome, everyone. During the course of the webinar, I want to cover these three main topics. So connections that could have been designed differently, so not to be, to be a bit PC. Then connections that failed or on the path to failure, so things to avoid. And then connections details that are worth noticing. But first, I just want to say that I just don't want to pick on negative aspects of someone's design. I just want to highlight the fact that some of the details that I've been observing need to, you need to consider them, and hopefully in your future designs, there will be better outcomes. So starting with connections that could have been designed differently. Well, I'm starting with some of them where, see, when I saw this one, I said, wow, so many bolts, and it could have been done in a different way. And then starting to look at this in a more detailed matters is, well, there's a metal plate connecting this member to the column, and then the height of this bolt group is definitely greater than anything that is allowed within codes if there's a shrinkage. So, in retrospect, you say the main issue with this one is in service. If there's shrinkage, there will be splitting in this connection, and any splitting would compromise the resistance of that joint if there's any actual load applied to this joint. This one, nothing wrong, nothing wrong in terms of resistance, but really, when I see this and I see the beauty of the wood, I say this could have been done in a different ways. So yeah, somebody made a killing in terms of supplying steel, but that's not what we want to see in a timber structure. But as I said, it works. So code wise, it's okay. This one's an interesting one. So it's a structure or a portal frame. So moment connection between the column and the beam. And when you look at it closely, we see another case of steel plate restricting the shrinkage of the timber member under reducing moisture content in the member. So there's a steel insert into the glulam at the top and at the bottom, and then dowels that are inserted between the steel insert and the glulam. You can see here the bolts that are connecting the steel insert to the plate, and then the other one at this portion. But the steel insert and the fact that everything is connected to the steel, and then the addition of in-service dry conditions, and we're talking about heated inside environment, and the moisture content of that member can go as low as 5%. So even though it's fabricated at 12 or fabricated at 8, the resulting moisture content will force shrinkage, and then we're starting to have these shrinkage cracks. Now, lots of dowels in both orthogonal directions, so it may not be that much of an issue, but it's not as effective as what it was designed from the start for this one specifically. Timber rivets, used a lot in North America, introduced lately in New Zealand. This is a photo of a truss where the rivets are utilized, and it consists of a steel plate connecting different members, and the rivets are inserted. Now, the requirement is that the flat side of the rivet is supposed to be installed parallel to the grain of the member. And this way, the fibers in the members are spread apart, and the gross area of the member is not compromised. There's no reduction, and the member retains its full tensile resistance. Obviously, this has not necessarily been communicated efficiently everywhere. And one can see that in this case, the rivets were installed at whatever orientation. And when I see this, well, the rivet did cut into the the fibers, there's potential for actually splitting the member. In this case, there was enough wood above that the member resistance was not compromised. You get the same thing here, another location, same project. So definitely an issue with the one of those installer that did not get the message. So things that need to be passed on into making sure that your design is actually implemented the way you want it. A very nice pedestrian bridge in Europe. It has quite nice features, structurally speaking. When one looks at it, it's composed of two triangular segments and allowing some adjustment on site depending on the position of the foundation. And the triangular sections are connected using steel weldment and dowels. When one looks at some of the connections, you see that, okay, there's a steel plate, and then one would, guess that there will be a steel plate along in the member. It's not showing at the bottom, so that's a nice detail. And when one looks at the those dowels, those last three dowels, the end distance in those dowels makes this connection very susceptible to brittle failures. So on the other side, the end distance is quite long. It may not be an issue, but as it has been tested, this small end distance will create an issue for that connection. On this footpath between two buildings, just want to highlight what I've observed in this connection. So it's a two connection with the members connected with two inserted steel plates. So what we have is two instances of wood, steel, wood connections. What I'm observe is the positioning of the steel plate. So when I look at this and using the European Gill model, say, well, it's the thickness of the side member that governs. In this case, for embedment, and the middle part here, if I divide it in two and use the same thickness on the outside, I say, well, there's a portion which is left out and not utilized. So either this was kept for fire protection, or it's just that, the connection or the positioning of the steel plate could have been more on the outside to give it or to utilize the outside portion of that member. There's some places where these dowels are dowel holes are filled, but it's not the case everywhere. So either it was this portion, the outside portion, was meant to provide some fire coverage, and then the dowel holes were just not filled, or it was not meant this way, and the position of the steel plate could be more on the outside to utilize the full volume of the member. Another connection where the strut is connected to the vertical member. And when we look at this, we have a steel plate. More than likely, the load here is in compression, so that steel plate is doing most of the work. But when we look in more detail, we have dowels that are also positioning the inserted steel plate inside the member. And we have again, moisture issue with shrinkage and the development of tension perclograin splits in the connection. Hopefully, it's not a connection that will be subjected to tension, so it's not that critical. But if there's tension force on that connection, then this is compromised. So potentially steel or screws could have done the same thing without the problem of splitting in the wood member. Problems that were noticed in the past. So my career is over 30 years. So when I started, chainsaw adjustments were done on site a lot. Nowadays, we don't see this as much because everything is fabricated in and prefabricated and done within very tight tolerances. But this, this cut for the inserted knife plate, definitely not a good one, and it led to some issues in the during erection. This one, for a project where the visual aspect of the connection was quite high in terms of demand, so everything was done with the requirement that the steel did not be apparent. So it was done very nicely, a lot of prefabrication, but in this case, some mishap during erection. It could have been corrected. It's unfortunate it wasn't picked up or corrected by the erector. It was, picked up by the inspecting engineer afterwards. This one, it's a design issue. So another older structure where the edge distance of the fastener, not a good one. So hopefully that was picked up during the project, and connectors were installed to fix the flooring member to the beam to make sure that this member on top would ensure that would stay in contact with the beam. So, and this is a detail that is reproduced throughout the throughout that building. So unfortunately, it wasn't picked up. Nowadays, we have 3D renderings that allow us to see these things coming, so we can avoid these things, these details. As I said, if perhaps it's not a structural issue right now. If there's vertical fasteners that are keeping the members above, and then all the resistance is still effective. Another building that I've been able to observe, this connection actually is not, there's no issues with this. And that's the example of what it should be. Definitely not this way. So this is same structure, a bit further along. still, in my opinion, the erector could have made sure that this visual aspect would not be picked up later on. Bolt hole misalignment. We are working to very tight tolerances, so timber manufacturers right now, are working to plus or minus 1 millimeters. So it's very, very tight. Hopefully these tolerances are communicated to the steel weldment fabricators. These things tend to happen before. There's potential for adjustment on site, but any enlarged timber hole will compromise the resistance of the fastener. Another noticed fabrication tolerance. The steel plate was meant to bear. Probably not. In fact, that you have dowels in here, so there's probably a steel plate that is inserted in the middle of the member, but it certainly doesn't look good. If I'd be in this case, I would have asked holes to be drilled in the steel plate and screw inserted to keep the plate in place, in contact with the wood. Moving on to connections that failed. First point that I want to show is where the connection failed because of inadequate resistance. We've probably all seen this one. That's a Velodrome, Scandinavia. The structure was supported by the roof structure was supported by timber trusses, and during the night, truss connection failed. The commission of inquiry was set up, and a net tension resistance failure was concluded. And unfortunately, that resistance was not verified during design, and it ended up this way. Luckily, no one perished. So nails or rivets will allow some. So if you're using nails or rivets, these are fasteners that do not reduce your gross area. So if you design your member, your member cross section, then you're okay at your connection. But any other fastener, there will be some reduction in your gross area. So you need to allow for some extra member sizes, because you will need to connect at the end, and you will be removing some material. Sorry. This one, an interesting one, a second story platform, fire escape platform, and at the top, the connection between the vertical and the horizontal member had failed. So definitely compromising the entire efficiency of this fire escape. You can see that just under the dead load of the structure, the remaining portion of all other connections are starting to fail as well. This structure has been repaired since. Connection at the bottom of a timber truss reinforced with pre-stressing or post-tensioning. In this case, the perp to grain resistance was not checked, and it started to crush, so compromising the effectiveness, long-term effectiveness of this post-tensioning. On one of these conferences that I've attended, we were brought to a case where timber structure had been designed, built, and been compromised after a few years in service. So you have this office portion of the building. It is cantilevering in this side, but supported with this strut. So everything would be, this portion would be hanging, but we're relying heavily on this strut in compression. And this connection at this point was compromised. So these were temporary supports were installed to make sure that there's no building collapse. And this is the good side, the good connection, and one can appreciate the distance between the end of the member and the top of the bearing plate on the concrete. But at the other connection, there was definitely something happening. So if we go back here, we have a bearing plate underneath, a steel plate inside, and a pin and some dowels. Probably those are just to keep the weldment in place. The main load transfer is through this steel plate underneath. And when one looks at it, some issues with that steel plate. These little added compression plates were put in afterwards. The strut end was strapped together to make sure that there was no splitting in the end member. But when we look further, we see that the steel plate has embedded into the end of the member and compromising the resistance. So inadequate bearing parallel to grain under probably wet conditions. I'm not sure exactly what was, if that was checked, but the remedial measure would call for probably a higher or larger bearing area. So moving from connections that fail to connections that are on the path to failure. And at this point, there's been a lot of talk about moisture management, but I want to make the point of long-term moisture management, so in-service moisture management. So this will lead to shrinkage, normally in enclosed structures, enclosed building. And these shrinkage issues will lead to resistance problem. This is a case where members are connected, and what I want to illustrate is the end of that member. So anytime that the end grain is exposed, we're asking for trouble. So this should be a no-no. If this is done for some reason, it should be protected by some whatever means. And then there's some older buildings in Europe where this has been, experienced and then corrected over time. Another point, another issue in this case where the end grain is exposed. This is we've all seen these buildings in Sweden, series of 8-story CLT buildings that were built in the early 2000s. So in this, at that time, timber was celebrated and timber was exposed. And unfortunately, well, it's not always a success story. So when you look closely at the balconies, look at the fact that the end grain again was exposed, and one can see the starting issue of some problem. This will lead to degradation of the resistance. And this is seen throughout the building. And that's just because, we wanted at that time to see timber. We were happy to see timber and to celebrate the fact that multi-story timber buildings were being done. Another example of where timber is celebrated, timber structure is celebrated, but not necessarily protected the right way. So it's a parking garage, so cars underneath, cars on top, and a lot of the timber is exposed. Unfortunately, it's exposed, but not necessarily protected at all the right location. So this is starting to have water issues, and then will lead to rotting, and it will compromise the bearing capacity of these beams over the column. So we need to take care of the end grain and making sure that we protect the members so that we have lasting connections. Some details that were added after these water ingress issues were noted. Hopefully that will change with time, but we'll see how it goes. When I started my career in the mid-1980s, I was asked to look at a lot of these old timber trusses that were built in the 1940s. Because of the timing that these were done, a lot of them were assembled with wet timbers and used over the years in Canadian climate. So enclosed structures, heated structures, and the moisture content went from probably over 20% to down to 5 or 8%. That's sometimes when we measured. So very significant shrinkage issues in these trusses member, and it led to a multitude of issues. A lot of them were just a lack of maintenance following the shrinkage, so they were all connected with split rings and shear plates, and it's just a matter of okay, shrinkage is going to occur, but make sure that there's a plan to go and retighten those threaded rods or bolts to make sure that the members are actually in contact, to make sure that those fasteners are actually working the way they were meant to work. Now, this may not be always possible to go and have access to bolts and fasteners and retighten them, so one has to plan for this. There's extensive amount of splitting in the members, and at that time we had to install anti-check bolts and clamps just to make sure that the members retain their resistance at the connections. A much newer structure in this case, this is a gymnasium, and in this case we have beam, glulam beam elements that are connected to other segments. To the left here, you can see the structural system is something like this. So you have a simply supported beam with an overhang, and then supporting the the other segment to the right. And then, so very nice determinate system, and there's no issues with this approach. Now, in this case, this is the supporting beam, and this is the beam being supported. There are steel plates inside the members, and dowels are inserted to connect the glue lam to the steel plate. And then the steel plate is extending to the other side, and then you have dowels again. The problem in this case is that we have one single steel plate from top to bottom. And if there's any shrinkage in that member, the dowels are keeping the top and the bottom of the steel to shrink and reduce in cross section. So we're starting to see splits along the member. And if you look at other places in that building, you had multitude of locations where the dowels had split. May not be catastrophic, but in this case, an expert opinion was called in after a year that the building was commissioned. So this looked a lot more serious in this case. And then, people wanted to know if this was an issue. It just doesn't look good. And there's ways to go around this. There's maximum height, maximum vertical distance, or maximum distance across the grain, where dowels should be installed to make sure that there's allowance for shrinkage if shrinkage is to occur. So it's a matter of fabrication, erection, moisture content, and then final moisture content in service of the member. All these things need to be taken into account. Same building, but in this case, it's the connection between the beam and the column. So we see the steel plate at the bottom, and then vertical plate inserted into the beam, and then dowels. So again, problems with shrinkage. The top and the bottom wants to shorten or not be as wide, and then there's split in the middle. Moving on to the last portion, so connections details that are worth noticing. First one is moisture management. And it's not only about moisture management during erection, but planning about what's going to happen afterwards. So I'm not sure that we're there yet in New Zealand in terms of moisture management during erection. So a lot of the other places do protect the members. So in this case, we have members that will be left exposed that are heavily protected during erection, and part of the structural members will not be exposed. So moisture management in this case is not that much of an issue. And then we see here that, okay, yes, it's delivered with a lot of protection, and then remove for erection and connection with other members. If that connection is exposed for a longer time, then that should be protected as well. And this is what we see, another case of this. And again, a portion of the wrapping that has been removed to put the connections to connect the members. And another example where the wrapping has been removed when the top surface has been connected to the top cord. Many examples in older buildings, so a covered bridge in Switzerland, They're renowned for those. Some of them are 500 years old. And okay, when we talk about end grain protection, well, we're talking about end of member being protected. So there's an added piece that are inserted to the end of the member to make sure that the wood end grain would not suck up the moisture or the rain that would come up on that piece. You recall the Swedish set of apartments built in the early 2000s in the same area. More recent timber buildings were built, more or less the same configuration, same balconies, but in this case, the timber is not as exposed. So there was definitely learning from the first set of buildings, and when one looked closely, everything was covered. So these are still timber balconies, but all of it is protected, and only the underside of the balcony platform is connections. Deep in this case, timber bridge in Austria with the end connections at the bottom of the struts, well protected with sheet metal that has been fixed to the connection. Make sure that water that can accumulate on the top surface will not drip into the end grain of the member, and sitting on all other members as well. End grain protection, so just adding end timber pieces to keep the visual aspect of timber, but we don't see any end grain in this member. Timber bridges, so timber arch, glulam arch, and glulam members, but all of it has been protected. So the top surface has been protected, and the connections have been protected as well. So no potential for accumulation of moisture on top of the member. The side member will get moisture, but it will drip and will not accumulate within the member. Other examples. So lots of moisture management in this case. And another example where exposed glulam members outside are being protected, and this is the detail of the sheet metal into the glulam. Other details that need to be noticed. So in this case, fire protection. So it is very common to have steel brackets that are exposed. So this one definitely this one was covered with intumescent paint. But if you don't like the look, okay, if the look of the intumescent paint is not desirable in your structure, well, one avenue is to conceal any of the steel bracketry. And this is what was done into that building. So all the steel connectors were eventually covered. Those dowel holes were plugged, and at the end you'd get something where nothing is shown. It takes a bit more detailing but it ensures that during fire, your steel brackets are not sucking up the high temperatures, and then your connections are not compromised. Some examples of redundancy. So nice designing approach in some cases. Football or soccer stadium in Eastern Canada. So in this case, it's 3-inch arches. So inch at the bottom, inch at the top, and then inch at the other end. Obviously, so nice connections, and one can see that the arch member is made out of 2 glulam laminations. The steel bracketry consists of steel plates inside, and there's the required number of fasteners to keep these members together, working together throughout the length. But what I want to show is this connection here. So we have a moment connection. The arch was made out of different segments. So we have one moment connection here. So steel plate that connects the bottom, and another steel plate that connects the top portion of the arch member, and probably another steel plate that connects the web. But what one doesn't see or doesn't appreciate here is that there's on the other lamination, the other connection is further down. So it's not at the same location that we have the moment connections. So we have redundancy in the connection because the connections in the 2 different laminations was not adjacent. So this ensures that we have some redundancy in the connection area for the arch member. Same principle in another building. In this building, it's more or less a flat roof system. In this case, the main structural system consists of beams spaced, so two laminations in the beam. The column is made out of 3 members. The 2 outside members are supporting the beam in bearing, and then the middle portion is continuing throughout and is ensuring the lateral stability of the beam system. But what was also very interesting is that in this system, so we have a beam system. This beam here, this beam lamination, is simply supported from this end and this one, and then has an overhang and then supporting this other one. So a Gerber system, and we have connection between the supported beam and the supporting beam. And in the other lamination, the other connection is further down on the other side. So what we have this kind of system. So a determinate system with the advantage of an indeterminate system. So for one lamination, we have simply supported beam with overhang and the connection between the supported beam and the supporting beam. And in the other lamination, we have the simply supported beam in the middle, and the connection is going to support the end segments. So we have our gravity loading bending moment diagram that looks like this, but the moment resistance envelope is only compromise for one of the lamination at these given location. There's always at least one lamination that can support the gravity loads, and that allows for variability in the loading. So you never know; you can't control everything. So the gravity loading can vary in location, and these points of minimum moment can vary in location, but you always have at least one lamination that is working in this case. So that's very clever. This is a case where we have a beam supporting another beam. So in the case, another case where this portion is being supported by the one on the left. So another case where the supporting system is this simply supported beam, and the one on the right is being supported. So similar to the other gymnasium example I showed you before, but in this case, two laminations, and in this case we have a support at the bottom, and then a support at the top of the supporting beam. So what we have a case of this kind of system. So bearing perp-to-grain at the bottom, and given it's the same species of wood, same detail at the other end, and the steel plate is just in between the two laminations. This is what we have. Connection at the top. So very simple, very effective, and no problems with shrinkage of the beam. So in summary, I just want to make sure that you could recognize that detailing is important to come up with an efficient design. I want to make a point about moisture and moisture management and moisture changes during the in-service of the building, and also protect the timber from moisture ingress at all costs, both during the erection and after in-service. Thank you very much, and I'm open to questions.
Thank you very much, Pierre. That was very interesting. It's great to see all the different photos of examples of connections. I'm sure many of us have only seen the few that we've designed or looked at, so it's really great to see a wide variety of what's out there. We have a few minutes for questions, and there's a few questions here. First question, what are some easy ways to avoid moisture problems causing splitting at the connections? Do we expect no problems if we have enough edge distance? I think this question is referring to more the internal stuff rather than the external exposed timber.
Yes, yeah, it's a good question. Yeah, it's not necessarily it's not a matter of the edge distance necessarily. It's really to make sure that the restrictions that we are imposing between a steel plate, the fasteners that are restricted by the steel plate, and then the timber member, the distance perp to grain is will be able to accommodate any potential shrinkage. Now, if it's a tight fit dowels connections, there's no way. There's no allowance for movement, so that will be an issue for sure if there's any shrinkage that will happen during in-service. If it's a bolted connection where the bolt hole in the timber and in the steel plate can allow some variation in movement of the connection of the fasteners, then one could allow a greater distance per grain between fasteners, between the extreme fasteners. but it's something that needs to be taken into account.
Thank you. We've got a similar question, so maybe we'll just follow up on that. Someone has said, in the upcoming 1720, clause ZZC for A 3.6, unless the limiting of shrinkage stresses perp to grain is considered, a single steel splice plate shall not be used for rows of dowels, bolts, or coach screws if the distance H max between the two outside rows exceeds 125. So that's what you're saying. Could you provide an example of how shrinkage limitations are addressed when timber connections are utilized in exposing areas allowing H max to exceed 125?
Use many. So obviously, the example of the gymnasium where a single steel plate was used between the two beams. This for me is asking for trouble. It will definitely lead to some splitting in the member. The last detail that I've shown, where you had a steel bracket that transferred the load between the beams in bearing, was a better design in terms of accommodating the potential for shrinkage, because there would be no restriction or very little restrictions. But the moment that a given steel plate and tight fitting dowels are used, and I understand it was the right way to do it in terms of resisting the load. You cannot put individual steel plates between the different horizontal dowels, from one member to the next. It wouldn't be efficient to transfer the load. So the single steel plate was the way to go in this case to transfer the force, but it leads to some issues. And it's, in this case, the expert opinion was called within a year of the building commission. So not a good thing.
Yeah. Someone's asked, so for that connection that you've shown with the bearing plates top and bottom, slide 101, I believe, would not shrinkage of the beam, would that cause the supported beam to drop?
Yeah, you would see it. You'd get the same, more or less the same shrinkage in both sides. So you probably would not see it. So not an issue really per se.
Would you end up with a gap between the bearing plate and the timber member at the top potentially, or?
No, because it's bearing. So yeah, you probably notice that the top of the supported beam is slightly lower than the top of the resisting beam. But this is it's not that much of a concern when you look at it. Everything is transferred through bearing.
Right. Okay. A few questions about protecting timber members from moisture. Someone's asked, I didn't see many painted timber used to protect the timber and joints. What are your thoughts of using coatings to protect timber members, especially end grain of exposed timber members?
Yeah. The protection of end grain. Well, if you can guarantee that your protection will last and will not have cracks itself, that's the main thing. So your protection has to be a lasting scheme. There's the acetylated wood, the Akoya brand that we see, where they did some tests on painting or protection coatings, where coatings can last longer. Perhaps this is one way to go, but this is not probably financially viable for all cases. So I would recommend some kind of other sheet metal protection, or timber protection, where the side grain of the timber is actually protecting the end grain.
Right. And I guess with the conversation around coatings as well, it has a lot to do with having a good maintenance schedule, which relies on
Right. Yes.
the
Yeah.
owner of the building, and that's not
Yes.
always followed through.
Correct. Yeah.
Yeah.
And that's always the issue. We
Yeah.
design things, but we need to design for the 50-year design life.
Yeah, exactly. We're almost out of time here, and there's still a few questions. I'll maybe just ask one or two more if that's all right with you, Pierre.
Fine.
There are many proprietary connectors available using full depth steel plates, for example, flitch plates, hook and loop type connectors. Do you have any comment on these with regards to splitting tendency at the dowels?
If yeah, there will be some issues. So it's they are designed for resistance. They are commercialized for resistance, but it's still the designer's responsibility to make sure that in-service conditions will not lead to splits. Your client, the owner, the user of the building, will not want to see this. So there has to be ways to restrict these splits. It's through moisture management. You either deliver to timber members to the moisture where it's going to be in service, and then there's no issues with splitting. But that's not necessarily feasible all the time.
Yeah, fair enough.
Yeah.
Someone's asked, are H5 treated timber poles with exposed end grains resistant to moisture effects?
I believe that the moisture may increase, but it's the fact that it's treated is just that it will not degrade. Yeah, I think moisture treatment is not a recipe against moisture changes. It's against the degradation of the fiber. Yeah.
Yeah, that makes sense. And maybe the last question, and then we're probably out of time for the day. Slide 101 still had some dowels, top, middle, and bottom. Would these not pose a risk of shrinkage, cracking?
Not so much the bottom ones or the top ones. I would be concerned with the middle ones, but they weren't that big.
Do you mind, Pierre, sorry, do you mind just going back to that slide so we can see which?
Sure. Yeah,
detail?
so these ones, these four ones, yeah. So you've got these ones, okay, so yeah, there's not a lot of shrinkage between these dowels and the bearing plate. Same thing at the top, but the dowels in the middle, okay, do pose a risk of shrinkage, because it's the distance. If there's any form of resistance in shrinkage, is the distance between these ones and the bottom here. So that's where the restriction will be. Your load will want to go all down on the bearing plate, and the top of this beam is going to be restricted by these dowels and want to stay up. So there's potential for split here, and same thing at the bottom. So here, if there's shrinkage, all the load is being communicated and be transferred to the top. And this portion here wants to shrink and go up, but it will be restricted by this one. So you probably get a split here and a split there, depending on the size of these dowels. Now, these, from what I could see, they're probably 1/4 inch, 6 millimeter in diameter. They were really small in terms of, when you look at them, not very big. In comparison to the other example, where in the gym, where the dowels were in the the range of 14 to 16 millimeter, and quite stiff. But in terms of these, yeah, they do pose the risk, but it's they don't seem to be that big.
Right. Great. I think that's probably all the time we have today. Sorry if anybody's questions didn't get answered today, but thank you very much, Pierre. That was a great presentation. And thanks everybody for joining us today. Have a good afternoon.
Okay, very much.